last time, I give you a brief introduction and outline of this course, emphasizing the phenomenology of a phase transition at the finite temperatures and also the important theory questions. And today we will go back to statistical mechanics as I promised and start to address these important questions, one step at a time. So here's what we start from this sort of a partition function in statistical mechanics that we can sum over all this exponential minus beta h, where h is a Hamiltonian of the system, and we can define a free energy in this exponent of this exponential function, e to the minus beta f, where f is a free energy. The phase transition that we are interested in has the property that the free energy of the system shows non-analytic properties as a transition. So we will define properly what this non-analytical properties is in just a moment, but let me just emphasize this relation between this Hamiltonian and the free energy. So the Hamiltonian of the system is the total energy of the system. In classical mechanics, this is just a sum over kinetic energy and potential energy. In quantum mechanics, it is sum over kinetic operator and potential operator. When we sum over all this probability e to the minus beta h and sum over all degrees of freedom in the Hamiltonian, we effectively can define free energy. In the exponent, when we talk the log of this trace of e to the minus beta h, we can define the free energy. So that's what we learned from the statistical mechanics. And the interesting property of this phase transition is that the h, the Hamiltonian, is an analytic function. However, the free energy can be non-analytic. Okay? In other words, we simply sum over all these degrees of freedom in the Hamiltonian, and then we can define this free energy. All these degrees of freedom in the Hamiltonian is actually analytic, but when we sum over degrees of freedom, we can have an analytic function as a temperature or as a tuning parameter. And that's exactly what happens at a transition. This sounds very weird, but we will address this issue later. So let me just remind you this definition of the first order and the second order transition. By Ehrenfest classification, it says that if we have an nth order phase transition, this quantity, this derivative of the free energy with respect to this control parameter, or this temperature of this tuning parameter G, has a jump, discontinuity at a transition. So this is kind of a very rough definition of first order or second order transition. And we will see that this definition is not entirely correct concerning this continuous or second order phase transition, because this continuous phase transition, because the specific heat, which is a derivative of free energy with respect to temperature, actually diverges. Not a jump, but a divergence at the continuous phase transition. So we will use the continuous phase transition instead of a second order phase transition for purpose from now on. This very important relation between this Hamiltonian and the free energy in this partition function tells us really something very deep about this phase transition. Sum over this analytic function, and you define this as a free energy, and the free energy shows non-analytical properties at the transition. So how come? So the non-analyticity of a free energy is encoded in this jumps or discontinuity of this nth order derivative of the free energy with respect to this tuning parameter. So whenever there's a jump or discontinuity, this is non-analytic or even divergence. So question number one, how can this expression give non-analytic behavior as a function of beta 1 over kBt? Right, so that's the big question. As I mentioned just now, this relation is actually equivalence between these two functions, and how can on the one side is sum over the analytic function, but on the other side, this function could be non-analytic. Question number two, how can the same Hamiltonian describes several phases simply by changing temperature. For example, in this magnetic example, the magnetization is actually 0 when temperature is greater than Tc, but this is non-zero for temperature below Tc. Okay, so we are using the same Hamiltonian. The solution of this problem shows that this magnetization is 0 when temperature is above Tc, but non-zero when temperature is below Tc. We are using the same Hamiltonian, but this Hamiltonian describes several phases, at least two phases, the high temperature phase and low temperature phase. The way that we tune the system to this high temperature, low temperature phase is by changing the temperature. How can this be done or achieved? Simply by changing temperature, and we could have these two different phases. Or in many other examples, we have more than two phases under the same Hamiltonian. Okay, so this is the question that we want to ask in this course. Question number 3, what does the mathematical model or theoretical model have to do with the reality? So the reality refers to experiments, and the mathematical model refers to theory. In other words, we could construct some theoretical model calculations like Landau mean field theory. What does this theoretical model calculations have anything to do with the reality, meaning the experiments or scalings and so on? So we need to make a closer link between this theory and these experiments. And this is also the topic that we will discuss. Examples that I showed you last time to illustrate this point, the relation between this theory and experiments. The liquid gas transition that we mentioned last time shows the power law dependence on the T minus Tc, the same exponent that we can see from this magnetic system, where this magnetization near the transition shows a power law behavior, and this power law exponents B and B beta is almost exactly the same, 0.32. However, mean field theory predicts that this beta is just 1/2. A systematic deviation between the theory and experiments. One may think that, well, this difference is not that big and it's pretty close, right? So 0.3 and 0.5 close enough. It's not a big deal, because oftentimes in theory we could quantitatively describe experiments by using some model calculations, and even in some cases we can get a quantitative agreement. But difference could be actually explained in terms of more refined theoretical models if we simply just add more terms to the Hamiltonian, or perform the more detailed calculations by keeping more terms in the Taylor expansion, for example, or in perturbation theory we keep more terms in our perturbative expansion. And the wishful thinking is that by doing so we may gradually improve our theoretical predictions, and then theory predictions will get closer and closer to the experiments. That's what we hope for. So we could refine our theory so that this will be closer to the experiments, and we can keep doing this refinement of the theory, and eventually this 0.5 from the mean field theory predictions get closer and closer to the experimental observation. So that's just wishful thinking. That's what we hope for. Unfortunately, in many cases in physics, things don't happen as we hope for. This kind of a difference is not unimportant. This difference is really important, because on one hand, the experimental technique could be further improved. We can more accurately determine these exponents up to, say, 2-digit or 3-digit or even more digit. As the experimental technique gets more and more accurate, and this difference is still there. So what can we do about this? We need to invent a more fundamental point of view that is very different from the mean field approach, and we will talk about that later part of this course, the renormalization group analysis. The RG, as I described last time, that we could either increase the system size and monitor how this coupling constant evolve when we increase the system size, or we could come from the high temperature and we start to lower temperature and we integrate over the higher energy modes of the system, and we monitor how this coupling constant evolve when we reduce the temperature and we remove the high energy degrees of freedom, and we could have some relations between this coupling constant before and after this so-called RG transformation. And this RG can really tell this difference simply by doing mean field theory, and you can improve the mean field theory. Unfortunately, no matter how hard you try, you cannot improve this mean field theory further, really get to this experimental results. You need something else that is completely different in concept than this mean field approach. An invention credited to the K.G. Wilson, and it is Wilson's effort and clever invention to construct this RG approach that allows us to get to this experimental observations closer and closer and resolve this difference. So let me just illustrate this point even further. The magnetization as a function temperature has features that the magnetization is lower as you increase temperature for ferromagnetic materials until this Tc is reached, and so this magnetization vanishes, right? What we are interested in here is that this magnetization as a function of temperature when temperature is very close to Tc. So that's what we probing here, so this exponent. So the mean field theory predicts exponent to be 1/2. This 1/2 exponent could be fitted into the data in this intermediate temperature range. Okay, this part of this data may be fitted to the square root temperature. However, temperature gets closer and closer to Tc, this kind of fitting doesn't work anymore. Another remark is that a small error in determining Tc experimentally allows this experimental data to be fitted to this square root behavior. In other words, suppose Tc is not here, but here this function actually changes to another power. So this brings us back to this previous remark that as the experimental technique gets improved further and further, people can more accurately determine this transition temperature, the location of the transition temperature, and so that this exponent could be more accurately determined. Okay? So there is no ambiguity between 0.3 and 0.5. It's always 0.3. So even experimental technique get further improved and innovated, so this number, this value, could only get more accurate. So this difference between 1/2 and 0.3 is actually systematic. No matter how hard you try, there's always a difference. So something new happens. Something new should be understood in terms of the renormalization group analysis. That is a universality or universality class. As I briefly introduced this concept last time, in this example, that the liquid-gas transition and the magnetic or spin systems shows exactly the same critical behaviors which have the same exponents, beta. So this phenomenon is called universality or universality class, which says that the same exponents and scaling functions to show up for a variety of systems. In many cases, there are more than 2 very different systems shows exactly the same critical behaviors, and all these systems show the same critical behaviors, belong to the same universality class. And this is really unique in this phase transition, and similarly different systems show the same critical behavior. So that we will address later. We could also think about the factors that determine this universality class. So what are the important ingredients to determine many different systems belong to the same universality class? So what the common feature that these seemingly different systems share and let them be classified in the same universality class. So the important ingredients to determine this universality class are the following. So suppose these two systems belong to the same universality class. They should have the same symmetry group of this Hamiltonian. Number two, the dimensionality has to be the same. And number three, whether or not the forces or interactions are short-ranged. Okay, so these factors determine whether these very different systems belong to the same universality class. First, the symmetry group of the Hamiltonian should be the same for different systems belong to the same universality class. And second, the dimensionality, say one-dimensional or two-dimensional or three-dimensional system. And number three, whether these interactions or forces are short-ranged or a long-range interaction. So that matters. So we will come back to this later. But this is just a more concrete definition of a universality class and the important ingredients of the universality class. So now let's talk about the scaling, because this is also a very important key concept in phase transitions. So the scaling shows up near the phase transition, and as I mentioned last time, for a system to go through the phase transition, we could take this experimental data of this observable, such as specific heat or magnetization or transport properties, and as a function of the temperature and also tuning parameter. For example, in this icing magnet near this critical point at Tc, we could measure the magnetization of this icing magnet near the phase transition as a function of temperature or reduced temperature, this magnetic field H. When the system is critical or near the critical point, this observable say a magnetization and can be put into this equation called the universal scaling functions. So let me just using this plot that you can see from your textbook, T to the power of times m times minus 1 over beta H divided by m delta. As we'll discuss later, if you plot your data near the phase transition of a magnetization, the field at the final temperature, and plot it in this fashion. Horizontal axis is the reduced temperature multiplied by the magnetization to the power of minus 1 over beta. The vertical axis describes the field divided by this magnetization to the power of another exponent delta, whereas beta and delta could be determined experimentally, or you could fit and fine-tune this values beta and delta so that all these curves collapse into one or two universal function, and which we call this phi plus and phi minus, describing the system above or below this transition. So, but before the data collapse, which means that if you don't plot this way and you simply just plot this data set in this conventional way, so you could get some different curve like this. So this is 1, 2, 3, 4, 5, and so on. 6. You measure this magnetization as a function of temperature at all these different fields, and you may find all 6 different curves in your measurement. And you don't know whether there is some relation among these different curves, but if you are clever enough to make a plot in such a way, you put this h divided by m to the power of h delta in the vertical axis, and the x-axis is actually t times m to the minus of 1 over beta, and you find that all this data or curves fall into 2 different groups, phi plus or phi minus. So all these curves could be either phi plus or phi minus. And all these data points, even though they belong to different curves, they all collapse into the same universal scaling function. And that's what this phi refers to. This is a universal scaling function near the transition, where observables shows the scaling or a data collapse behavior. This is really dramatic and surprising, but people, experimentalists, discovered this scaling form experimentally, and theoretically, starting from this free energy scaling, possible scaling property emerges from this free energy. So Edward Wheaton scaling hypothesis, coming from this free energy, scaling ends up the free energy, which we'll discuss later, and starting from the free energy, which shows that scaling properties, and you could derive some sort of a universal scaling functions from Edward Wheaton's scaling hypothesis. So this scaling function is really something important and has significance both in theory and experiments. From both sides of physics, this is really dramatic and really deep because something universal happening. Okay? Suppose two different systems, they belong to the same universality class, and they should have the same universal scaling functions near the transition, no matter how different they are. And these exponents are exactly the same for the systems that belong to the same universality class. So universality class is tied closely to the scaling laws or universal scaling functions that we mentioned here. So we will talk about this in more details when we get there. So let's come back to the partition function, and we try to address these questions that we proposed earlier. The starting point is this question: how phase transition occurred in principle. So what is the principle that leads to the phase transition? This is a many-body problem and at finite temperature. So the only guiding principle from physics is the statistical mechanics, right? So in classical phase transition, we don't have deeper foundations than the statistical mechanics. But the question is, how can the phase transition derive from this statistical mechanics? So let's come back to this statistical mechanics. So the purpose, the goal of the StatMech is to compute the partition function. Z is defined as this trace e to the minus beta h. H is Hamiltonian, which is equivalent to sum over all the states, the eigenstates, e to the minus beta e states, and E is the eigenenergy of the system. Okay, so of course this is quantum mechanics, but E could be just the energy of a given state. So this energy comes from Hamiltonian of a given region. And the volume of the system is given by L to the power of D, where L is system size, as D is the dimensionality of the system, and the surface area of the system is proportional to L to power of D minus 1, and this omega refers to spatial regions where your Hamiltonian is defined. In principle, this partition function Z is calculable if the system is finite. When the size of system is finite and volume is finite, everything is finite, so the partition function could be computed. We need to worry about this boundary condition. So for example, for a finite size lattice, and we need to impose a periodic boundary condition that connects two sides of the lattice like this and also like this. Suppose particles or atoms sitting on the lattice point. So we need to connect these edges, two sides of the lattice of equivalent positions, make them equivalent to fix the bounding condition. So that's the periodic bounding condition, or other bounding condition, and so on. We will look at this in more details and find out the phase transitions occurred only when the system size becomes infinitely large. Okay? At any finite size, there's no phase transition. However, when the system size gets larger and larger until so-called thermodynamic limit, when this volume goes to infinity is reached, then the free energy can be non-analytic and the phase transition can occur.